So I welcome all of you to this lecture on terahertz spectroscopy, and very good morning to some of you, very good afternoon to some of you, very good evening to some of you, and maybe very good night to some others. And now I welcome Professor Michael on behalf of University of Lucknow and on my own behalf and on behalf of our physics department, University of Lucknow. And I was planning some collaboration with Professor Michael, and I was planning to visit his group in the September as a Fulbright fellow. And I hope maybe we have to postpone this due to present situation of pandemic. And in the soon the situation will improve and we will continue our collaboration or start a new collaboration. So briefly, I will tell you about Professor Michael. He is very renowned in his field of terahertz spectroscopy. And Professor Michael, he is working as a professor in the University of Vermont, Department of Chemistry. He did his Ph.D. from Syracuse University and then worked as a postdoctoral fellow at University of Cambridge. And his research interest in application of terahertz spectroscopy in different areas, material science or biological or pharmaceutical, all type of applications of terahertz spectroscopy. And Michael is he is recently selected for the 2019 Forbes 30 under 30 science group. Okay, that is very prestigious. Being in 30 under 30 of the Forbes is very prestigious. And for his outstanding contribution in the terahertz spectroscopy, he is recipient of Young Scientist, recently received the Young Scientist Award from IRMMW-THz organization for spreading and expanding the translation of terahertz spectroscopy from its core community into the chemical sciences. And recently his research group received that NSF grant. And now I welcome Professor Michael to please start his lecture. Professor Michael, please.
Thank you, and thank you for having me, and thank you. I'm so happy to see over 100 people here. I think this is one of the few good things to come from these crazy times is that we can connect. And I would just encourage anyone think of questions throughout my talk, and if you have any questions afterwards, I'm happy to answer any emails. So I'm always open to looking for new ideas and new collaborations. So keep that in mind. So just to give you a kind of overview of what I'm going to try to talk about, I'm going to start off talking about what terahertz is. And by the end of my talk, you might be so tired of hearing the word terahertz because I'll say it so much. But it's this really important tool that we're finding that's useful for solid state characterization. And then I'll go through a few different applications. Depending on time, I might not get through all of them, but we're finding lots of cool applications for terahertz, and I'll try to highlight some of these things. And so the whole kind of idea and why we're doing this is that we are looking at the properties of solid state materials, and we're doing this because all around us, solids are being used for a wide variety of applications, And some of the areas that we're personally interested in are materials for flexible displays, making screens bendable and flexible. And these are these organic semiconductor materials. So these materials that they're not inorganics, it's not crystalline silicon, but it's an organic molecule that is a semiconductor. Can everyone see my screen and everything? You can see the animation? Yes? Yeah, cool. Okay. Another area that we're interested in is porous materials. And an application here is in gas sequestration, gas storage, fuel cells, even going beyond to chemical separations and toxic chemical removal. And we're looking at these types of solids that form these voids in the crystal structure. So these are called, this particular material is a metal organic framework. And so what that is a framework where there's a big void space indicated by this kind of blue ball, where gases can come, adsorb, and get trapped in there. And another thing that is a solid that's in everyday life are pharmaceuticals. And so we are very interested in the properties of pharmaceutical materials, pharmaceutical solids, and why that leads to certain properties on a bulk scale. But what the key is in all of these applications, and in every single solid state, material science, condensed matter physics field, it's this combination between what molecule you have. So what's the molecule, what's the geometry of the individual molecule, how that molecule packs in the solid state, so how the molecules kind of pack together in the condensed phase. And that's where people kind of traditionally stop and you say, okay, there's a structure property relationship, right? That's always, you always hear structure property relationship. But what's missing from that structure property relationship are the dynamics. So whenever you pack molecules, wherever you have molecules, things are moving. Atoms and molecules are vibrating and moving around. And so I like to say it's a structure property dynamics relationship. And all of these three things go together to drive material function. And so the goal of my research and my group's research is to understand what these fundamental dynamics are. So what are these motions that are occurring in the condensed phase? And then what motions contribute to material function and material properties? And to do that, we use terahertz radiation. And so what is terahertz radiation? Terahertz, it falls between the microwave region and the mid-IR region of the electromagnetic spectrum. It can be called far IR on occasion. We're talking about frequencies of about 0.1 to 10 terahertz. That's wavelengths that are squarely in the millimeter wave length scale. And if there's any chemists out there, this is roughly about 10 to 300 wave numbers, inverse centimeters. So that's kind of the units we're working in. And what makes terahertz kind of valuable is it borrows properties from both sides, its neighbors in the EM spectrum. So on the microwave radio wave side, it borrows the fact that a lot of materials are actually transparent to terahertz radiation. So terahertz passes through things. But on the infrared side, more the optical side, we can do spectroscopy with it. So, and the spectroscopy that we do is vibrational spectroscopy in the condensed phase. You can also do rotational spectroscopy in gases, but we focus on vibrational. Terahertz is a relatively new field, relatively. Every year I say that I feel like it's getting less and less new, so I probably shouldn't say it anymore. But there were problems in the 80s that were fixed about generating and detecting terahertz radiation that gave it kind of a name known as the terahertz gap. That's not really true anymore. We have the methods to generate and detect it kind of really well established. So now we're in the phase of applying it. And so there are so many applications to this type of radiation that I've just kind of highlighted on this slide. One cool one that I'll just kind of mention is communications. So everyone's hearing now, you know, the 5G revolution. We're going from 4G to 5G, and that's the next big thing for cell phones. Actually, going beyond 5G, the next phase goes into the terahertz region. So there's a lot of work out there on incorporating terahertz antenna and terahertz receivers into mobile devices or into routers for home use, and that promises speeds up to many gigabits per second. So I saw an application where you could download a video before a flight in a second with a terahertz receiver. The problem is that atmospheric water absorbs terahertz really strongly, so there are very specific frequencies that this will work, but that's a work in progress. But what I'm going to focus on mostly is spectroscopy. And just to kind of prove to you that terahertz does go through things, I just went into my lab and I stuck different materials in our beam, and we got measured signal out in each of these cases. So cardboard, fabric, and drywall. Each gives us a measured terahertz electric field, which is what we're measuring. Actually, I'll explain that next. But we get signal through all these. And the difference that you notice with drywall is the waveform is spread out a little bit. That's just because the thick piece of material with a high refractive index, and so that stretches out the electric field in time. And it is a time axis. So we do this in the time domain. And this is sort of animation that, let's see if it wants to play for me. Okay. It does not want to play, I don't think. Okay, but the basic kind of setup that we do here is what we actually measure is the terahertz electric field in the time domain, and we do that by dragging two pulses across each other using a delay stage. It's similar, very similar to an interferogram from FTIR, but it's not the same thing because we're actually measuring a terahertz electric field. But by taking a Fourier transform of this electric field, we get a terahertz power spectrum. And if we do this for a sample and a blank and then take a ratio, we end up with an absorption spectrum. Or you can get transmission. It just depends on how you process it. But everything I kind of show you from now on will be a terahertz absorption spectrum. But this is always the workflow. So we do it in the time domain. We have a sample and a blank. We ratio them to get the absorption spectrum. Okay, so the whole point is why? Why are we doing this? Like I've said, terahertz vibrational spectroscopy is very similar to FTIR, Fourier transform infrared spectroscopy. The same underlying theory, it's still harmonic oscillator solution to the Schrodinger equation and all of that nice stuff. The difference is that in the mid-IR with higher energies, you are probing strong force constants or strong interactions. And what I mean by that is usually covalent bonds. So we're looking at intramolecular motions. On the other hand, when we go to lower frequencies, that means we have a lower force constant, a weaker interaction, and so it's more intermolecular motions. So intermolecular non-covalent vibrations. An example is kind of here, and this is an organic semiconductor rubrene, where this is a kind of a traditional terahertz mode. And if you look closely, what you see is this entire phenyl side chain, all four of them on this one molecule, flop around, right? It's not just two atoms vibrating very, very quickly. It's the entire molecule is moving. The entire backbone is sort of flopping like a bird's wing. So these are large amplitude motions, very complex. But what that means is we're exploring a large area of the potential energy hypersurface. So we're really kind of exploring out all these degrees of freedom in a single terahertz vibration. And so this information really samples bond strengths, intermolecular bond strengths, angles, the strength of dihedral angles, and so on, all in one kind of shot. One of the really powerful things about terahertz is it is extremely sensitive to very weak forces. And what that means is that if I have crystalline polymorphs or materials where it's the same kind of molecule, but they pack together slightly differently. And on this slide, what we have is glutamic acid, the basis for MSG. And the molecules are almost identical. There's a slight rotation of the dihedral angle right here and here. But you see, they both have carboxyl groups. They both have OH bonds. So if I made these two crystals, which I can in the lab, they're stable and I can make them, and I bring them to an FTIR, I'll see the same spectrum basically for the two of them. There might be some slight shifting between one peak by a few wave numbers. The same thing with Raman. If I put it in a Raman spectrometer, they'll look nearly identical, maybe slightly different, but hard to discern. But what you see here on the left are the terahertz spectra in blue, and they're completely different. You know, there's no question, you know, the beta form has a big peak right here that doesn't exist in the alpha form at 1.3 terahertz. And so terahertz spectroscopy, even though it's a probe of forces, really is what we're doing. We're probing the intermolecular forces. Those forces are so highly dependent because they're so weak, those non-covalent forces are so highly dependent on the structure that different structures will always give you different terahertz spectra. And that's really important. And that's really useful because you can use terahertz spectroscopy kind of as a complement to X-ray diffraction. And what's nice is X-ray diffraction may take you a half hour per measurement, whereas terahertz, we acquire data at 15 hertz. So I can get 15 waveforms measured in a second. And so that's really nice. So it's really fast. We don't have to grind the sample too much or anything. We can get really nice data. But it also leads to its biggest problem. The biggest problem with this technique. If you remember, if you dig really deep to when you took maybe organic chemistry when you were in school, and you had to memorize those tables of all the transitions, okay? OH bond, 3400, carbonyl, 1600, CH stretch, 3000, et cetera, et cetera. So you can use FTIR as a kind of method to determine, okay, I have an alcohol, I have a carboxyl, I have a carboxylic acid. You cannot do that at the terahertz, in the terahertz range. So no matter how great I am, no matter how many awards I win for terahertz, if you gave me a terahertz spectrum of an unknown sample and said, Mike, what is this? I can't tell you. I would have no way of being able to interpret that, because each of these peaks is totally unique to the unique packing that exists in that one structure. And so one of terahertz spectroscopy's greatest strengths is also one of its greatest weaknesses. And so the way we get around that and the way we address it is we do computational modeling, and we do density functional theory and quantum mechanical simulations, which are these black lines on this spectrum. And so what you see is if we do this well, we get an almost perfect agreement with the experimental data. Doing these simulations is the right way is very, very, very important. So if you are working with a crystalline solid, and I've just I think I've hopefully made it clear that it's these long range forces, these weak forces that are really important at the terahertz frequencies, you need to take those long range forces into account in your simulation. What that means is you can't use Gaussian to do these simulations. You can't take a single molecule and get out an accurate terahertz spectrum, because like I said, some of these motions are intermolecular, many things moving, so one molecule won't do it. Two molecules won't do it, right? Because if you have two molecules, you have two molecules in a vacuum, so they're not experiencing the forces from the other molecules in that periodic crystal. And we have a paper coming out soon where we made clusters up to I think 36 molecules with 1,000 atoms, and we still never got the right terahertz spectrum out. So this is my I'm preaching to everybody out there, whoever does terahertz, do not use isolated molecule simulations if you want to get accurate terahertz spectra. You have to use periodic boundary conditions. And what that means, and what we do, is we simulate basically the contents of one unit cell. We actually even reduce it further by taking symmetry into account. So we simulate the symmetry independent unit of a unit cell, and then that unit cell has translational symmetry in all 3 dimensions. And we take that into account in our simulations through Bloch's theorem. So we simulate the unit cell, and then we do some math tricks to replicate that in all 3 dimensions. But what that means is all of the forces in that simulation are real. It's a real periodic method. The assumption in this case actually is that we have an infinite solid, which is a much, much better assumption than saying we have a 10 unit cells, because these forces are very long range. They fall off in some cases 1 over r or 1 over r squared, so very, very slowly. And to do that, we use Crystal 17, which I helped develop, and CP2K. We do ab initio molecular dynamics. So we do this all quantum mechanically, all first principles, with very, very little to no empirical input. So all ab initio. And for anyone who cares, the way that we do it is basically the solution to the harmonic oscillator shown in your equation, E equals h bar omega for the transitions. Omega is actually the force constant, so intermolecular forces over the reduced mass. And what really is kind of the important or the costly bit in the calculation is this Dij term. And so to do that, we need the second derivative of energy with respect to displacements. And so we do this numerically. Typically, we build the force constant matrix, and then we diagonalize it, and we get out the eigenvectors and eigenvalues. So for the most part, I think everything I present today is within the harmonic approximation, but we do some work in the anharmonic regime, which I won't really get into today. Okay, so that was a very long introduction, but what this does for us is really powerful, because if we do the experimental spectroscopy, and if we get a really good agreement with that experimental spectroscopy with our simulated spectral result, that means that our simulation is doing an excellent job of capturing all of the forces in our crystal, the weak forces and the strong forces, because if the strong forces are wrong, then the weak forces will also be wrong. And so one really obvious next step is if you have all of the vibrations right, and so that means you have the terahertz spectrum modeled correctly, that means that all of your thermodynamics must also be right, because the thermodynamics directly depend on the vibrations. And so if I do my Terahertz experiment and I do my theory and everything matches, I can trust my thermodynamic parameters, my Gibbs free energy, the entropy, enthalpy, all of this, without going and doing thermodynamic experiments, because it has to be right. If the vibrations are right, the thermodynamics have to be right. And that's where some things that we've done where we've predicted the stability of polymorphs really shines, because we can use all of this together to get some really important information. Okay, so starting with the results now. And I'm going to start with, this is something very recent from my group. I think I just got this figure on Friday, but it really highlights the power of terahertz as a structural tool. So this is a metal organic framework. You see it makes this kind of, there's a metal node here. We have some organic linker, and it makes these pores in here. And in these pores, there's some debate over what is in there, but I think it's pretty clear that we know now that there's some 2 water molecules that go into those pores and adsorb, and they have some hydrogen bonding. But what isn't clear is the symmetry of this structure. So there's ambiguity with whether the water molecules are symmetry independent or not. And if they are symmetry independent, we have it in the CC space group with a small kind of symmetry unique unit. If the waters are independent, we have a larger symmetry unique unit, but the bulk structure is exactly the same. It's just if the water is slightly breaking symmetry or not. That's the question. The powder X-ray diffraction patterns for these 2 cases are identical, because it's such a subtle change in the structure, whether that water molecule is symmetry independent or not. So if you look, the 2 structures are overlaid here. They're identical. You can't make the difference out using X-ray diffraction. However, if we simulate, so this is the experiment on the right. We took this in my lab at 50 Kelvin, and it matches the powder X-ray pattern, the experiment. But if we simulate the frequencies using the 2 different space groups, we get 2 very different terahertz results. And that's because the terahertz transitions are related to how many symmetry unique atoms there are. So it's 3n minus 6 is the number of vibrations, where n is the number of atoms. So we have a smaller symmetry unique unit, you have less IR active vibrations, and so less peaks. If you have a bigger symmetry unique unit, you have more IR active vibrations and more peaks. And so that's what we see, where only the P21 on C, or the lower symmetry structure, predicts vibrations down here around 1.5 terahertz, which we see over here. We see some modes down here. where the CC space group doesn't predict anything until 1.7 terahertz, which starts about here, right? So this result is still not good, and we're still optimizing what theory we use, and this is very preliminary, but it just goes to show you how sensitive this tool can be for structural identification. So we're even X-ray diffraction, which people would say is kind of the gold standard for structure, this highlights that in some ambiguous cases, terahertz is useful. Okay, cool. Now into some of the really cool stuff, I think. Some of the stuff I really like. So we've been working with these materials, organic semiconductors, because they're kind of new materials. They have a lot of promise. You can make these materials in low cost, high volume synthesis because you can do it in a beaker on a benchtop, as opposed to crystalline silicon that needs to be, perfect, and it needs to be manufactured at high temperatures, and there's a lot of manufacturing steps. These organic semiconductors are easily spun into thin films, so that's where the flexible displays come in. They're great options for solar cells, new electronics, and so on. One of the things that limits organic semiconductors is their charge carrier mobility. So whereas inorganic semiconductors will have charge carrier mobilities of thousands to tens of thousands of centimeters squared per volt second, organic semiconductors are somewhere between 0 and 10. So very different scales here. And the goal of inorganic semiconductor research is to make that charge carrier mobility as high as possible to really make more efficient devices. And there's a lot of things that go into the charge carrier mobility. There's temperature and defects and all of these things. But one particular fundamental intrinsic property is the atomic dynamics. And where that comes into play is scattering of free carriers off nuclear motion or electron-phonon coupling. This is particularly true for the lowest frequency vibrations because they're very thermally active, right? So if we have a terahertz vibration of 20 inverse centimeters, thermal energy at room temperature is 207 inverse centimeters. So that vibration, that terahertz vibration, will be excited, 20 states will be excited at ambient conditions. So this motion is really occurring at a large amplitude at ambient conditions. And so here's a place where just having coffee with some people and talking really led to an awesome collaboration. So I was actually still in Cambridge, and I met these guys and girls over coffee, and they showed me this paper that they had just published, where they were looking at reducing dynamic disorder, so reducing electron-phonon coupling in organic semiconductors by suppressing large amplitude thermal motions. And so this large amplitude thermal motions, I see that and I just change it to terahertz motions because they're the same exact thing. What they originally did before they met me to kind of show that there were these large amplitude motions, where they took a series of crystals, organic semiconductor crystals, and they did electron diffraction of thin films. And they analyzed the streaking in the diffraction dots, in the diffraction peaks. And that streaking is a measure of how much motion there is along that direction. And they showed that as you, in like this case down here, these BT-BT and C8 BT-BT, as you alkylated the core, semiconducting core, they saw a reduction of some motion and an increase in the charge carrier mobility. But that's about as much as they could understand. They didn't know what motions there were. They just knew there were motions in one plane of the material. And so that's where we met, and we started talking, and I said, okay, how long did it take you to do these electron experiments? And they said, well, it took about 2 years to get all the data. And I said, okay, give me your samples and I'll have terahertz spectra in a week. And that's what happened. So much easier to do terahertz than it is to do diffraction experiments. And so we did the terahertz spectroscopy, and everything on the terahertz is on the left here. And you see is the dotted lines are the theory result. And you see in some cases like rubrine up top, The theory and experiment are perfect. They are almost spot on. In some cases, not so much. If you kind of look over here, we see a bit of a disagreement between these two peaks. I want to emphasize that we're talking differences of 5 wave numbers or like 0.2 terahertz or 200 gigahertz. So this is very, very small deviations. It could be that if we cooled the samples to a lower temperature, that peak would sharpen a little bit more and shift. So that doesn't really concern us in terms of the accuracy. And also on the right is inelastic neutron scattering, where you see when you look over a larger frequency range, the agreement is beautiful. It's kind of spot on. So we simulated the spectra. We took experiment, and then what we have, each peak here, each stick is an individual motion type, right? So we can go through and we can look at the motions. And what we saw and what we were interested in were these type of longitudinal motions, because that's what we thought was really impacting the electron phonon coupling. Okay. And so this slide has a lot going on, and I'll kind of just walk you through it briefly. So we took 2 materials, this time a DNTT, which is on the top here, and the alkylated version, so C8. So there's an octyl group on both sides of the DNTT. And you see DNTT column is kind of on the right here, and the C8 is on the left, on the right here, and the DNTT is on the left. Sorry. This first 2 panels is just the amplitude of each vibrational mode as on a mode by mode basis. And so what we see, there's this 1 over frequency squared dependence. And so as we increase the frequency, the amplitude in real space decreases quadratically, which is what we expect. What you see in here actually is the unweighted fluctuation in the charge transfer integral on a mode by mode basis. So we just took each vibration, we displaced every vibration a constant amount, or every mode a constant amount, and we calculated the fluctuation in the charge transfer integral. So basically how much that motion is going to scatter the free carriers. And then the ultimate result, which is on the bottom here, is the product of these first 2 panels, essentially. So because as if the motion is lower in frequency, it's going to move more, and so that it's going to have more electron phonon coupling the more motion there is. And that ultimately leads us to this bottom panel, where the red line is the integral. So it's the total electron phonon coupling of all the modes, but each bar is the individual modes, how much they contribute. Okay, what we found was that both materials exhibit this longitudinal motion, okay? And that longitudinal motion is detrimental to electron phonon coupling, or is detrimental to charge carrier mobility. As you see, this green bar here is relatively large contribution. In this case, it's very, very large contribution. But what was interesting to us is that the alkylation made no difference between the 2 systems. It was the same, almost the exact same frequency. And the theory was that alkylation hindered that motion, and that's why it led to a larger charge carrier mobility. What we found was that actually that's not true. And the thing that actually helps is that what you see over here in these 2 modes is a torsion of the semiconducting core, okay? And that torsion, those torsions play a significant role in the unalkylated system and contribute quite strongly to the overall detrimental type of interactions. What alkylation does actually is it shifts the frequency of those torsional modes to higher energies. And by shifting them to higher energies, we reduce the amount of thermally activated motion, which reduces the value of the product, for example, of E and F, and reduces the overall effect, basically. And so what we really found, though, is that, you know, what's the kind of a powerful result is that in this material, by calculating it, we've found one single motion that contributes about 90% of the bad electron-phonon coupling in these systems. And so we can look into why, and if we kind of look at the orbitals, what's happening is in the equilibrium position, the orbitals of two adjacent molecules kind of line up in phase. But as you translate the two molecules, that leads to the orbitals lining up out of phase, which effectively traps the free carrier, and that ends up reducing the ability of the carriers to move through the system. There's some debate out there over the overall mechanism and if it's band-like or hopping. I won't get into that, but this is a cool result. And what we found was that if we hypothetically increase the frequency of that one vibration, of that longitudinal vibration, we increase the predicted charge carrier mobility by quite a bit. So what we're really working on is understanding what motions play a role in this phenomena, and then how we can engineer new molecules to stiffen particular coordinates to increase the frequency of those vibrations, to reduce the amount of thermally activated motion, and thus increase the positive properties. And so we think of that as a phonon engineering, as kind of a new field of study where we can get into some new stuff. I'm just going to skip that. Okay. So we actually developed a new material and we synthesized it in our lab. And what we have here, we thought, was that we can increase the pi conjugation off to the side chain by adding these thiophene rings. So we have our semiconducting core here, and then we have a sigma bond, and then another aromatic system, and we were hoping that we could kind of join the aromatic system together. What ended up happening, though, was that sigma bond, so this sigma bond right kind of here, is able to rotate. We did increase the pi conjugation across the entire side chain, but then that freedom of rotation ends up opening up a new type of vibration. So instead of this longitudinal vibration, now we have this torsional vibration that's really detrimental. And so we've plugged one hole and another three holes have spouted in the boat. And so we're trying to understand kind of all of this. Okay, completely changing gears and going in a different direction. I'm going to talk about phase transformation phenomena in molecular crystals. And so I'm going to talk about this material, camphor. Camphor has a crystal to disordered crystal transition at 244 Kelvin. And what I mean by disordered crystal is that the molecules are localized in a site, they're ordered in their sites, but they're free to rotate or do what they want. So it's sometimes referred to as a plastic crystal or disordered crystal. But the terahertz spectra of the ordered phase is these red and green dotted lines, and you see we have nice spectral features, and that's common of a crystalline material. But the solid lines down here, the solid red lines, are the plastic crystalline terahertz spectra. So it's a disordered crystal, there's no discrete transition, and it's not really easy to be understood. So we decided to kind of look into this. And so what we did was we took the low temperature crystalline phase, and we ran a molecular dynamics simulation, ab initio molecular dynamics. So we used quantum mechanics, and we let everything relax. And so what happens is the molecules started kind of moving past each other, again in the same kind of longitudinal type motion. While we let the system run through its molecular dynamics trajectory, we monitored the angles of the simulation. And so we started with an orthorhombic cell, 90, 90, 90 degrees. And then we just watched what the unit cell did, or the simulation cell. And two of the angles stay around 90 degrees. They oscillate a little bit, but they stay right around 90 degrees. where one of the angles makes a straight shot for 120 degrees and then stays there again. So we kind of reach equilibrium over here, right above 22 picoseconds. Okay, so right away, I look at that and I say, okay, I have a hexagonal, and now I have a hexagonal cell. So something interesting is happening. But if you look at this kind of picture down here, this is a snapshot from that molecular dynamics trajectory. It looks disordered. You know, it doesn't look like a nice crystal like the first picture or this picture. It looks like a mess. But we looked really closely at it, and what ends up happening is the molecules do kind of stay in one place, but they rotate around and they do their own thing. But every once in a while, the dipole moments arrange. Okay, and so you see that kind of highlighted in these two molecules where the two oxygens are pointing in different directions, and so you have an arrangement of dipoles. The angle between these molecules matches a hexagonal cell. So what we did was we just basically extracted this dimer and fit a unit cell around it, and then generated a crystal structure, and then optimized that crystal structure. And so what's really cool about this is as we used a more physical model, we got a much better agreement with the X-ray results. And let me explain what that means. So this is a crystal because the molecules do sit in crystalline sites, and so it does diffract. But there are not many diffraction features because we're just diffracting basically off a ball of electron density. Because they're disordered. So we only get these few features, and the experiment is in blue, and it's kind of hard to see, but the experiment's in blue. If I just take this extracted crystal structure without doing anything, and then do a solid state DFT optimization to get to this kind of structure, that would represent an ordered 0 Kelvin structure because I'm using static density functional theory to optimize it. So that's 0 Kelvin. And what you see if I do that is this dotted line. So I get the 3 kind of features or the 4 features, but they don't line up with my experimental result. Okay, I can do a little bit better if I take the DFT optimization and constrain the unit cell to a higher temperature volume, and then do an optimization again. And that would be with what you see with the black line, which gives me almost a perfect agreement with the blue line, with the experiment. So we're almost there, but the most accurate method was actually taking all the positions from the molecular dynamics simulation and averaging them, and then generating a powder X-ray pattern. And that's the red line, which agrees quite nicely with the experiment. So depending on, as we got more physical in our computational model, we got better agreement with the experiment. Okay, just to kind of wrap this up. So we've got the structure. We can simulate the dynamics using both the molecular dynamics, which basically what we do is we let the simulation run, and then we just look at the dipole moments, and we generate an IR spectrum by taking a Fourier transform of them. Or we can do a static DFT simulation where we displace every atom statically, and then generate eigenvectors and eigenvalues. And so what you see here is these are the experimental results in solid, and the molecular dynamics results in blue. And you see we get a good agreement for both the crystalline form, which is in blue, and the disordered form, which is in red. But over here, what we have is the experimental data in solid, the molecular dynamics simulation in dotted red, and then the DFT simulated, where we get actually the eigenvectors and eigenvalues in black. And what was interesting to us is the higher in frequency we went, things started to agree between the two methods. But at the low frequencies, even though there are some peaks predicted from the DFT, from the static DFT, they're not the same intensity as the molecular dynamics. And so to understand it, it actually was a really interesting phenomenon. What it was if you look at this first mode here, the vibration that's occurring is this translation, right? This translation of two molecules with respect to each other. In a perfectly ordered crystal, like what I have in the animation here on the right, what's happening is that these molecules, over the course of that transition, the dipole moments overall for the unit cell cancel, mostly cancel. And that leads to a low predicted IR intensity, IR absorption, because the IR absorption depends on the change in the dipole moment. But when you have a disordered crystal where every dimer is it's in its own orientation, and you have this motion, there is not such a large net cancellation of dipole moments, which leads to a larger observed IR active transition. And so that's why the disordered crystal model does a better job of predicting the intensity. It also turns out that this vibration is the phase transition mode. And so what we could do is we could do a simulation at different temperatures, fit an Arrhenius plot to it, and we can work out the activation energy for the transition, which is fine. But we could also work out this pre-exponential, this A term, which is a collision frequency, right? And we can do it in both directions, from high temp to low temp, and from low temp to high temp. And the predicted collision frequencies of 0.5 terahertz and almost 2 terahertz beautifully match the experimental frequency of that particular type of motion, that longitudinal translational type of motion. So again, this is just a cool thing that's showing everything is linked here. The vibrations are linked to the phase transition. The phase transition is linked to the vibrations, and it's a bit of a chicken and the egg kind of situation. We could also predict the thermodynamics, and that's all fine. The last thing that I will talk about is a little bit of pharmaceutical stuff, just to finish up. And we've done a lot of work on disordered crystal or disordered materials, amorphous solids. And so if you look at these two kind of schematics of a terahertz spectrum, the crystalline material has these nice peaks, has these nice, peak here, a peak here, a peak here. Whereas the amorphous material is featureless. It's just this broad, featureless background. It turns out that broad, featureless background actually has a lot of information in it that we can extract if we know what we're looking for. And one thing that we looked at was the terahertz type of motion of a dihedral angle kind of flipping around. And so the dihedral is highlighted here in blue, right down here in blue. And I'll start with this plot here. So what we did in amorphous materials, there's this thing called the glass transition, and there's two glass transitions that we care about. There's a secondary, which is TG beta, and there's a primary, which is TG alpha. And what we found was if we tracked every dihedral angle in this amorphous sorbitol simulation above the glass transition, so I think at 300 Kelvin or 350 Kelvin, these are the red lines in this figure over here. What you see is that the molecules jump between, these well-defined regions. So there's these three well-defined regions, and at high temperatures you see that some of the dihedral angles are jumping between regions. Whereas at low temperatures below TG beta, for example here, the dihedral angle just kind of oscillates around and stays in one place. And that's really important. And it's also a terahertz vibration. And so we use this information. If I just, animations don't want to show. But what we actually showed is that there's a direct correlation between, so I should say that this TG beta, the motion only stops below TG beta. The motion only, the transition between these bins only stop below TG beta. So what we showed was that there's a correlation between, there's no correlation, as shown here, between TG alpha and the stability of the amorphous state. So if we make these molecules amorphous, we leave them out, this molecule here, nifedipine, crystallizes instantly, whereas this molecule here, which has the same glass transition temperature, primary glass transition temperature, crystallizes much more slowly. On the other hand, if we plot the stability as a function of the beta temperature, where these types of motions are frozen out and aren't allowed to happen, we get a clear correlation. We proved that this was true by taking that really unstable material, this nifedipine, and storing it at temperatures slightly above and below that secondary glass transition temperature. So I really want you to focus on sample C and D. So sample C was stored at 228 Kelvin, which is 23 Kelvin above the beta transition temperature. Sample D was stored at 193 Kelvin, which is 12 Kelvin below the beta glass transition temperature. Sample C was stable for 4 days by X-ray diffraction before it started showing crystalline peaks. Sample D, which was stored just slightly below the beta transition, was stable for, when we made this figure, it was 120 days. By the time the postdoc left who was doing this, it was like 2 years, I think. So stable for a really long time. I don't think my video will play here. I don't think my video will play. That's a shame. But what really is cool, the really cool thing that we did was then we took amorphous materials, amorphous pharmaceuticals, and now we know that, okay, the motions that are related to crystallization are stopped if we cool it below TG beta. We know that. And we also know the motions that we stop are also terahertz motions. So these dihedral type motions are terahertz vibrations. So our idea was, okay, let's use terahertz radiation alone to stimulate crystallization. And that's an interesting idea because what we're dealing with is not very strong radiation. So this is right now in the air, there is terahertz radiation flying around. It's going through you. You don't realize it. It's not harming you. It's not very strong. And so what we did was we took amorphous drug. We cooled it down in a liquid nitrogen cryostat to 80 Kelvin, so well below the secondary glass transition temperature, where it would be stable forever. It would be stable indefinitely. We put some temperature probes on it to monitor the temperature. And then we put it in a very strong terahertz beam. We monitored the temperature throughout the whole experiment. The temperature did not significantly go up. The terahertz did not induce much of a temperature change. But what it did induce, and what you see kind of in these screenshots, is that the red circle is the beam diameter, and it's actually it's a Gaussian beam, so it's the full width half max, and that's why in some of these pictures it extends, the effect extends out a little bit. But this is the terahertz beam diameter exactly. We actually measured when we made the figure, and what you see is that the terahertz is inducing a change in this amorphous solid, and that change that's inducing is a disorder order transition. So it's actually crystallizing the drug inside this region. And what's really cool is that when we heat the sample back up and we let the outside crystallize normally, we get two different crystal structures, two different polymorphs. And so what that tells us is that the terahertz radiation is inducing a change in this solid, and we have the possibility of controlling what final crystalline form we get out of our sample if we have it in a terahertz beam or not. And I think that's a pretty cool result and something that we're actively working on. So with that, I would just like to thank everyone that's contributed, my group at UVM right here. Still work really closely with collaborators at Cambridge. The pharmaceutical stuff was done with Copenhagen. Crystal, the code we use, is developed in Torino in Italy, so work really closely with them. And do some of the experiments. I didn't really show them here, I guess, but the camphor stuff, yeah, the camphor stuff was done with Brown. And with that, I'm happy to take any questions. Thank you very much for listening. I guess maybe I should unmute. Oop. What happened? I can unmute. I've unmuted you.
Yeah.
Professor Tandun.
Okay. Could you please my video also? You have stopped my video also. Okay. Yeah. Okay.
Are we back? Should I make you the host?
You can make me the host. That is better. Yeah.
Okay.
Yeah.
You are now the host.
Okay. Yeah, now it is better. So, Michael, thank you very much for very, very informative lecture in a very simple language. And now maybe I invite some questions from the participants. And I see in the here we have the head from Meerut University, Professor Birpal Singh. I welcome him on behalf of our university. Dr. Vineet Gupta from Hungary ELI. He is working on terahertz spectroscopy. He's here. Professor Yash Dwivedi is with us. So now I invite some questions. I think there are some questions. If there are some questions, please drop in the drop box. Okay, just in the chat box. Vineet Gupta has some question. Okay, I'm just unmuting him.
Yes. Hi, Michael. Can you listen to me?
Yes.
Yeah.
Thank you very much for this very wonderful talk. I am from extreme light infrastructure, and I'm also working in high field terahertz spectroscopy. So it is very nice presentation. And in your paper, last slide, you shows that the high field can change the crystal structure. So is it possible to do the calculation to see the effect of the high field terahertz spectroscopy?
Yes. So this is a very interesting and active area for us. And I will say that I don't think we still fully understand the mechanism. And so we are trying to understand precisely what it is that is inducing this crystalline change, or for example, we don't know right now if it's frequency dependent. So if we go with different frequency terahertz, we get different polymorphs. We don't know. I've had some discussions with colleagues where maybe, even though it's not heating the sample, we're going in with such an ultra short pulse with high energy that it leads to like an instantaneous heating or maybe a coherent heating effect. I know a paper just came out where they speculate that it might be a shock wave effect. So again, we're still working on it, but one area that I'm personally very active, that my group's working in, is identifying those phase transition modes. So like I discussed with camphor, and then targeting those materials. So, okay, we know that this particular motion leads to a phase transition. So can we hit at that frequency and induce a change? So that, again, it depends on, we can get the shape of the potential, we can get, all that information, but we're still, we've also used a free electron laser for those experiments. And that obviously when you get time, you only have maybe 2 days to do experiments. So I am building in my lab a high field terahertz source right now to do these experiments in-house with a 7 millijoule per pulse, 1 kilohertz rep rate amplifier to try to get some really high powers. So very active area that I don't have all the answers to.
Okay, so that's good. I would like to contact you again and for this.
Sure. No problem.
I was working with Professor Poonam Tandon, and we have a DAD project in Marburg with Professor Martin Koch.
Okay.
And so that I am here in extreme light infrastructure, and so working in high field terahertz spectroscopy. So I would like to contact you further for this.
Anytime. That sounds perfect.
Okay.
And thank you very much again for this.
You're welcome.
Thank you, Vineet. There is some question from Ayush Shukla. He is asking me to unmute. I am trying, Ayush, to unmute you. Yeah, okay. Ayush, you are unmute now. Ayush.
Myself, Ayush Shukla. Sir, good evening, sir.
Yeah.
Sir, myself, Ayush Shukla from University of Lucknow, Department of Physics. I have two questions.
There is some echo in your voice. Could you please speak more clearly? Yeah, Ayush.
Yes, sir. Sir, I have two questions. Is terahertz radiation dangerous? And the second question is that, can you give me an idea regarding terahertz wave propagation in human body, any model or any experimental measurement to get some sort of idea?
Michael, he's asking about terahertz radiation movement in human body, some experiment or something. Yeah.
Okay. Yeah. So the biggest thing with terahertz is it's very, very strongly absorbed by water. So the penetration depth for humans or for skin is very small, micrometers. So that kind of limits in my opinion, limits the utility of terahertz radiation for biological applications. That being said, there is a huge area of biomedical, biological terahertz research out there, but often they have to do things like take cells out of the body and grow them or embed them in some sort of matrix. It's very, very difficult to do this in vivo because of the water.
There is some comment, maybe you can see Mohit Gautam. If we consider low frequency cutoff notch, say filter, say 5 centimeter inverse in dispersive confocal Raman microscope, then can we call it as a terahertz spectroscopy? There's some question maybe in the message box. From Mohit Gautam, there is a.
I don't see the question, but well, can you just repeat the question? I'll try to answer it.
If we consider low frequency cutoff notch filter, say 5 centimeter inverse in dispersive confocal Raman microscope, then can we call it as a terahertz spectroscopy in Raman?
Yeah, so I don't present it here, but we also do low frequency Raman down to shifts of, like you said, 5 wave numbers. I don't know if that technique has an established name in the literature yet. So the two that I see most often is low frequency Raman or terahertz Raman. I personally prefer low frequency Raman, but that's just my opinion. But yes, so low frequency Raman is a complement to terahertz spectroscopy, just like mid-frequency Raman is a complement to FTIR or mid-IR techniques. Mm-hmm. And so in my lab, it was delivered and half set up right when the pandemic hit. So we have a confocal Raman microscope that can go down to 5 wave numbers, and it also has an AFM, so we can do tip-enhanced low-frequency Raman, which we're really excited about. And so it's just a complement to terahertz.
It means it is preferred to call it as low frequency Raman rather than terahertz Raman. I have read it in some papers. They coin a word as terahertz Raman also. Yeah.
I think both are fine, right? It's just preference, but both are used.
Mm-hmm. I think the last question we can have from Pankaj Kumar Singh. He has some question. So Pankaj, hello? I have unmuted you. Pankaj Kumar Singh, yeah.
Yes, madam, please. Yes, myself Pankaj Kumar Singh from ITVHU. My voice is audible?
Yes, you are audible.
Yes.
Michael, you have given a very wonderful lecture. One question I am having that is there is PHZ-TDS system. Can you explain in 1 or 2 sentences about the PHZ-TDS system? Thank you.
I didn't miss what system?
PHZ-TDS system.
I'm really sorry. I can't. understand
I can explain the full form. That is the Terahertz vibrational. The Terahertz TDS. That's the time domain spectroscopy.
You want to know about the experimental system?
Yeah.
Ah, okay. No problem. So if I just get here, I can get back to it. Let's see. Okay, here. Now my video is playing. So really how it works is kind of this video will show is we have an ultra fast laser, which is over here, this Oxford physics, which is Oxford physics. And we have a beam splitter. Terahertz gets generated on this, this green chip in this animation. The sample is this blue chip. And so what happens is terahertz gets generated, goes through the sample, but we also pick off a little bit of our 800 nanometer original pulse. And that goes on a delay stage. And then what we do is the terahertz radiation hits this nonlinear crystal here, this orange crystal, and induces a birefringence. And then we overlap the 800 nanometer pulse on that crystal at the same time as the terahertz pulse is going. And we actually measure the optical properties of the 800 nanometer pulse. So that's coming through this delay stage. And so what that actually does, the terahertz introduces a birefringence. We measure the polarization of the 800 nanometer pulse, and then we delay through in time. And what that does is it allows us to sample the whole terahertz waveform on a point-by-point basis in time. If that helps.
Okay, so I think there are some question. Michael, could you read in the box, the last one?
Which one?
Question 1 was from Swaroop Ghosh. There are 2 questions. He has written me privately, maybe. Okay. Okay. Maybe I will share it again. Copy it and share it.
Okay.
It is a private message, so maybe you cannot read it. Should not be private. And yeah, this one.
Okay. How does one understand the structural phase transition from terahertz structure? Okay, so if I just go back to those slides. I go back to these slides. So what we've found, again, using the simulations, is that this phase transition proceeds along a path marked by these arrows, right? There's a red arrow and a blue arrow, and it represents the 2 layers sliding past each other. Like I've kind of said, that is a terahertz vibration as shown here. So what we do, and how we really kind of knew that this is related, is from this pre-collision frequency, which is in the Arrhenius equation, which matches the exact transition frequency of the vibrational motion that matches the phase transition pathway. So that provides some confidence. And the other thing that we watched was the peak shifts a lot more as a function of temperature than any other peak, which, as you can see, we're going from 0.5 to 1.9 terahertz. So most things maybe shift by 100 or 200 gigahertz. This shifts by 1.5 terahertz. So over the course of the phase transition. So those things together provide kind of a lot of confidence that terahertz mode is responsible. And then your question about Caro-Parrinello molecular dynamics. This is where we get into nomenclature. The only thing I don't know, there's Caro-Parrinello molecular dynamics, ab initio molecular dynamics. What is important is that all of the forces are computed quantum mechanically, and that they are updated at each time step. If you use classical molecular dynamics, where it's required that you input bond force constants before you run the calculation. If you do a vibrational analysis, you're going to get out whatever information you put in. So if I said the OH bond has a force constant of whatever, 400 Newton meters, if I do some math, I can tell you exactly what frequency that will vibrate at, because it's the energy of the vibration is h bar, the square root of k over the mass. And k is, if I say k is 400, the mass is fixed. So if you use classical molecular dynamics, whatever information you put in, you get out. If you use ab initio methods or first principle methods, the fact that those forces are updated at every step means that you're getting much, much more accurate force information, which means much, much more accurate vibrational information.
So I think there are some very general questions. Maybe people can contact you directly by
Sure.
mail or
And
So-
email, anyone can email me. You know, I'm pretty easy to find on the internet, or I think you can Google me.
So thank you very much, Michael, for very nice and very informative lecture and giving your valuable time to us, to our students. And I'm very much thankful to all the participants who have like so patient to hear and be with us in this lecture. And thank you very much, Michael. Thank you.
Thank you very much, everyone, for having me and inviting me and staying up late to listen to my talk. Thank you, everybody.
Thank you, Michael. Maybe we will soon see us again.
Hopefully.
Not online, by the offline. Okay.
Yeah. Keep me posted on if you hear anything from Fulbright.
Yeah. Okay. Thank you, Michael. Thank you.
Thanks, everybody. Have a great evening.
Yeah.
Bye.